experimental testing. The multiverse is highly controversial, but its foundation is certainly solid. When we observe the universe today, it simultaneously tells us two stories about itself. One of those stories is written on the face of the universe today, and includes the stars and galaxies we have, how they are assembled and how they move, as well as their composition. This is a relatively simple story, and is the story we have learned simply by observing the universe we see. But another story is how the universe became as it is today. And that is a story that requires more effort to uncover. Certainly we can observe objects at very great distances, and that tells us what the universe looked like in the distant past. The light arrives today, having been emitted long ago. But we need to combine that with our theories of the universe, the laws of physics within the framework of the Big Bang, to explain what happened in the past. When scientists do that, they find compelling evidence that our hot Big Bang, the event thought to have created the universe as we know it today, was the result of a prior phase, cosmic inflation. However, to explain some puzzling phenomena in the universe, such as why empty space has energy, and why cosmic growth is not uniform, scientists have had to explain them with an idea called the multiverse. This is why physicists overwhelmingly assert that the multiverse must exist. Going back to the 1920s, new evidence became clear that not only were those spirals and ellipses in the sky entire galaxies, but the farther away scientists observed any particular galaxy, the more its light was systematically shifted to longer wavelengths. Although initially there were many alternative explanations, they all vanished with more abundant evidence until only one remained. The universe itself is undergoing cosmic expansion. Yet the universe today is expanding and the radiation within it is shifted toward longer wavelengths and lower energy. Then in the past, the universe must have been smaller, denser, more uniform, and hotter. As long as any amount of matter and radiation is part of this expanding universe. The idea of the Big Bang yields three clear and general predictions. First, a large-scale cosmic web with galaxies that grow, evolve, and cluster more richly over time. Second, a low-energy background of blackbody radiation left over from when neutral atoms first formed in the hot, early universe. Third, a specific ratio of the lightest elements, hydrogen, helium, lithium, and their various isotopes, exists even in regions that never formed stars. All three of these predictions have been observationally verified, and that is why the Big Bang reigns supreme as the leading theory of our cosmic origin, as well as why all of its other competitors have vanished. However, the Big Bang only describes what our universe looked like in its very early stages. It does not explain why it has those properties. In physics, if you know the initial conditions of a system and the laws it follows, you can predict extremely accurately, within the limits of computational ability and the inherent uncertainty of the system, how the system will evolve in the future. But what initial conditions did the Big Bang need to create the universe as we see it? Scientists have discovered that there must have been a maximum temperature significantly lower, at least about 1,000 times lower than a pi scale. This is where the laws of physics break down. The universe must have been born with density fluctuations of nearly equal magnitude on all scales. The expansion rate and the total density of matter and energy must have been balanced almost perfectly. To achieve an accuracy of at least about 30 million significant digits, we must have been born with the same initial conditions. The same temperature, density, and fluctuation spectrum everywhere, even in locations without causal connection, and its entropy must have been much lower than today. by a factor of trillions raised to the power of trillions. Whenever scientists face the question of initial conditions, they only have two choices. The first is to invoke the unknowable and say, that's just how it works. Because this is the only way it could happen and we cannot know anything more. Or we can try to find a mechanism to set up and create the conditions we know are necessary. The second path, that is what physicists call dynamical attraction, where they try to devise a mechanism that accomplishes three important things. First, it must reproduce every success of the model it is trying to replace, in this case, producing the Big Bang. All previous achievements must be produced by whatever mechanism scientists propose. Next, it must explain what the Big Bang could not do. The initial conditions that the universe started with, the problems not explained by the Big Bang alone, must be explained by any new idea that comes along. Finally, it must make new predictions that differ from the predictions of the original theory. And those predictions must lead to some observable, testable, and measurable consequences. The only idea that scientists have that meets these three criteria is the theory of cosmic inflation, which has achieved unprecedented success on all three fronts. Essentially, inflation says that before the universe became hot, dense, and filled with matter and radiation everywhere, it was in a state dominated by a very large amount of energy inherent in space itself, a form of field or vacuum energy. Except, unlike dark energy today, which has a very small energy density, equivalent to about 1 proton per cubic meter of space, the energy density during inflation was enormous, about 10 to the power of 25 times greater than dark energy today. The way the universe expands during inflation is different from what we are familiar with. In an expanding universe with matter and radiation, volume increases while the number of particles remains constant, and therefore density decreases. Since energy density relates to the expansion rate, the expansion slows down over time. But if the energy is intrinsic to space itself, then the energy density is constant and so is the expansion rate. The result is what we call exponential expansion, where after a very short time interval, the universe doubles in size, and after that interval it doubles again, and so on. In a very short time, a region initially smaller than the smallest subatomic particle can be stretched to be larger than the entire observable universe today. During inflation, the universe is stretched to an enormous size, which accomplishes many things. One of them is stretching the observable universe, regardless of its initial curvature, to be indistinguishable from flat. Take any initial conditions that existed in a region that began inflating and stretch them across the entire observable universe. Create tiny quantum fluctuations and stretch them across the universe, so they are nearly the same on all distance scales, but slightly smaller on smaller scales as inflation is about to end. Convert all that inflationary field energy into matter and radiation, but only to a maximum temperature much lower than the Planck scale. Create a spectrum of density and temperature fluctuations that exists on scales larger than the cosmic horizon, and it is adiabatic and isotropic everywhere. This reproduces the successes of the non-inflationary hot Big Bang, provides a mechanism to explain the initial conditions of the Big Bang, and makes a series of novel predictions that differ from a non-inflationary game. Starting from the 1990s and up to today, the predictions of the inflationary scenario align with observations unlike the non-inflationary hot Big Bang. The issue is that there is a minimum amount of inflation that must occur to reproduce the universe we see. And that means there are certain conditions that inflation must meet to be successful. We can model inflation as a hill, where as long as you are on top of the hill, you will inflate. But as soon as you roll down into the valley below, inflation ends and converts its energy into matter and radiation. If you do this, you will find that there are certain hill shapes, or what physicists call potentials, that work and others that do not. The key to making it work is that the top of the hill needs to be sufficiently flat in shape. Simply put, if you treat the inflationary field like a ball on top of that hill, it needs to roll slowly for most of the inflationary period, only accelerating and rolling quickly when entering the valley, causing inflation to cease. Scientists have quantified how slowly inflation needs to proceed. This tells us something about the shape of this potential. As long as the top is flat enough, inflation can work as a viable solution for the beginning of our universe. But now, this is where things get interesting. Inflation, like all fields we know, must inherently be a quantum field. That means many of its properties are not precisely determined but have probability distributions. The more time you allow to pass, the more the distribution spreads out. Instead of rolling a ball-like point down a hill, we are actually rolling a quantum probability wave function down a hill. At the same time, the universe is inflating, meaning it is expanding exponentially in all three dimensions. If we take a 1 by 1 by 1 cube and call that our universe, we can observe that cube expanding during inflation. If it takes a very short time for the size of that cube to double, it becomes a 2x2 by 2 cube. That is, it takes 8 original cubes to fill it. Allow the same amount of time to pass and it becomes a 4x4 by 4 cube. It takes 64 original cubes to fill it. Let time pass again and it is an 8x8 by 8 cube with a volume of 512. After only about 100 doublings, we would have a universe with about 10 to the power of 90 original cubes in it. Now, as far as we know, suppose we have a region where that inflationary quantum ball rolls down into the valley. Inflation ends there, that field energy is converted into matter and radiation, and what we call the hot Big Bang occurs. This region may have an irregular shape but must have sufficient inflation to successfully reproduce the observations we see in our universe. Then the question arises, what happens outside that region? Here is the problem. If you require that there must be enough inflation for our universe to exist with the properties we see, then outside the region where inflation ends, inflation will continue. If you ask, what is the relative scale of those regions? You will find that if you want the regions where inflation ends to be large enough to match observations, then the regions that do not end inflation will be exponentially larger, and the disparity worsens over time. Even if there are countless regions where inflation ends, there will be countless larger regions where inflation continues. Moreover, the different regions where it ends, where hot Big Bangs occur, will all be causally disconnected, separated by more inflating space. Simply put, if each hot Big Bang occurs in a bubble universe, those bubbles simply do not collide with each other. What we end up with is an ever-increasing number of disconnected bubbles as time passes, all separated by a perpetually inflating space. That is the nature of the multiverse and why scientists accept its existence as a default position. We have ample evidence for the hot Big Bang, and the Big Bang starts with a set of conditions that come without a physical explanation. If we add an explanation for it, cosmic inflation, then that inflating space-time has revealed and created the Big Bang, which would generate a set of novel predictions of its own. Many of those predictions have been borne out by observation, but other predictions also arise as consequences of inflation. One of them is the existence of countless universes, of disconnected regions. Each region has its own hot Big Bang, collectively forming what we call the multiverse when you combine them all. This does not mean that different universes have different rules, or laws, or fundamental constants, or that all possible quantum outcomes you can imagine occur in some other part of the multiverse. It does not even mean that the multiverse is real. Because this is a prediction that we cannot verify, validate, or falsify. But if inflation theory is a good theory and the data proves it, then the multiverse is not only possible but also inevitable.